Going to do is we're going to take the limit of f of x over g of x as x approaches, and sometimes when we want to look at the behavior, we could do the plus or minus positive infinity. So we're going to look at the behavior as it approaches both of f of x over g of x. All right. Now here's the thing. According to our properties of limits, I could do this exact same problem by taking the limit of f of x as x approaches plus or minus negative, or plus or minus, what, how would you say it? Positive or negative infinity, all over the limit of g of x as x approaches positive or negative infinity. Okay. So we're going to do this two ways. The first way is to write everything out and then take the limit. So what I'm going to do is I'm going to say the limit as x approaches positive and negative infinity of 3x to the fourth minus 2x cubed plus 3x squared minus 5x plus 6 all over 3x to the fourth. Okay, I'm going to do this graphically. I'm just going to plug it in the calculator and see what it looks like. So I'm going to come in here and clear this out. Remember that the numerator and denominator should have parentheses. That's the only way the calculator can determine what's the numerator and what's the denominator. So let me try this. 3x raised to the, whoops. Oh, it won't let me do it that way. All right, fine. Raised to the fourth minus 2x raised to the third plus 3x squared minus 5x plus 6, and then I'm going to close the parentheses, divided by 3x to the fourth. And I just graph it. Now as I look at this behavior, and let me make sure that I graph this properly, because my graph looks a little different than the one in the book. So let's just check and make sure. Yeah, it looks okay. Let's make sure that I entered in the equation correctly. 3x to the fourth minus 2x plus 3x squared minus 5x plus 6 divided by this. So we're going to look at the end behavior. Alright, I think I did it right. Let's just go with it. If I hit trace and I start to approach negative infinity, what does it look like my y value is approaching? 1. Okay. So now let's go the other way. There's a reason for that, right? And I'll explain that to you in a second. So now we're going to start to go towards positive infinity. Now I want you to look at this carefully. It's a little different, but what does it look like it's approaching? 1. Okay. It looks like it's approaching 1. But it comes up from the bottom, right? But it's approaching 1. Okay. So we are going to say, just based on the graph, now, I don't know if you guys remember this. This is a pre-calc algebra 2 thing. The reason it's approaching 1 is, and I want you to think about this in your head, as I start to plug in values, as we start to approach infinity, really big numbers, when I raise something to the fourth power, so just imagine in your head, 1 million raised to the fourth power. That's a 1 followed by, what is that, 24 zeros? And then it'd be times 3. So it'd be like 3 followed by 24 zeros. what happens is the rest of these terms are kind of insignificant. Right? And so this is our leading coefficient on the top, which is x to the 4th degree. Well, on the bottom, I've only got one term, but it's the leading coefficient. But the same thing would apply if I had a polynomial. So as we start to approach infinity, these remaining terms become less and less significant because I'm raising this to the 4th degree. When I take, I'll approach infinity much quicker in that leading coefficient term, the leading term, than I would the remaining other terms. Right? And by the way, once you start to get to infinity, you know, like infinity plus 6 might as well just be infinity, right? Well, infinity plus 5 times, or minus 5. Do you guys understand the concept that when we approach infinity, either positive infinity or negative infinity, the only thing that matters are the leading terms of the numerator and the denominator? Well, since those terms are going to be multiplied by the leading coefficients of f of x and the leading coefficient of g of x, then the ratio of those two leading coefficients is basically the limit. So what I'm looking at is 3 over 3, which is equal to 1. So sometimes we'll call this a horizontal asymptote, but in this particular unique case, it's not quite a horizontal asymptote, but that's the end behavior that we're looking at. Okay? Does that make sense to you guys? Mm-hmm. Okay. Now, there's another thing that you could do too. Your textbook actually wanted you to confirm that algebraically. And so you could think of this as a division problem, right? Like you could think of this as like 3x to the 4th going into 3x to the 4th minus 2x to the 3rd minus or plus 3x squared minus 5x plus 6. Now another way to look at that too is you could have done this. You could have said the limit, and we'll do this later on, and if you're going to be an engineer, you'll do this a lot in Calc 2. I could have rewritten it as 3x to the 4th over 3x to the 4th minus 2x to the 3rd minus 3x to the 4th plus 3x squared over 3x to the 4th minus 5x over 3x to the 4th plus 6 over 3x to the 4th. I could do it that way too, right? Well, this first term becomes 1, and then 3 of these cancel with this, but I'm going to have a number over infinity, so what does this approach? 0. 2 of these cancel with 2 of these, so I've got 3x squared on the bottom. What does that approach? 0. Here, one of these x's cancels with one of these, and I've got x cubed on the bottom. What does that approach? 0. And then the same thing here. I've got 3x to the 4th on the bottom, so I basically got 6 over infinity, which is approaching 0. So because the denominator for the remaining terms algebraically cancels, or the numerator, the remaining terms cancel because the denominator is a higher degree, all of those values will approach 0 if I were to separate it algebraically. So then what would the limit be? 1. So there's 2 ways to approach that.
Wait, why are they 0?
Look at this here. Alright, so if I have negative 2x to the 3rd over 3x to the 4th, when I reduce it, I've got 2/3. 3 of these cancel with 3 of these, and I've just got 2 over 3x. Well, if I plug in infinity, I've got negative 2 over 3 times infinity, and that approaches 0. Does that make sense?
Yeah.
So all these terms here will approach 0. That's why they're insignificant. That's why I could say, these don't mean anything. Because when you approach infinity, they literally mean nothing. That's their value. Because the bottom blows up so much faster. Okay? Any questions on that one? Now graphically, I could have done this the other way too, and I'm not sure we're going to because of time. But I could have taken the limit, right, of f of x and the limit of g of x as x approached to infinity, and then compared the two. But we'll do that at another time, okay? We'll do that another time. Actually, you can't. Well, that was the point that I was trying to make, is this works when we're approaching a value or a number. Right? If you look at the properties, we said x approaches c. And so this wouldn't work. That was what I was trying to prove to you. So I'm not even going to do it today for time's sake. Okay.